Hello, this is Hassan. I'm presenting our work Representation Learning with a Statistical Independence to Mitigate Bias. A central challenge in practically all machine learning applications is how to identify and mitigate the effects of the bias present in the study. Bias can be defined as one or set of external protected variables that distort the relationship between the input and the output variables. If we build a model to predict the output from the input variables, not considering the potential bias, it may lead to erroneous conclusions. The two most prevalent types of biases are dataset bias and task bias. Dataset bias is often introduced due to the lack of enough data points with respect to the protected variables. Task bias, on the other hand, is introduced by intrinsic dependency between protected variables and the task. Our method aims at learning features that are invariant to the bias protected variables in both cases. To design our method, we first looked at a typical end-to-end training scheme. Feature extractor FE learns features F based on which the classifier C successfully predicts the target. We add adversarial component BP to force FE to learn features that are invariant to the bias protected variable. Prior work focused on binary or categorical variables such as domain labels. Our method provides a solution for all types of variables including continuous and ordinal variables such as age and skin shade. We use a batch level loss function based on correlation coefficient between the actual and predicted bias protected variables. The classifier uses a regular cross-entropy loss with an overall min-max objective like GANs. Our method guarantees mean statistical independence between the learned features and the protected variables using the proposed vanished correlation scheme. Refer to the paper for the details and the theoretical analysis. This architecture can remove the dataset bias by removing the effects of B from F while F is predictive of Y. However, in the case of task bias, there is an intrinsic correlation between the bias and the output Y, which prevents the model to obtain the set of proper invariant features. Therefore, we use a method used by traditional statistical modeling and only incorporate adversarial head on the subset of the input samples that are invariant to Y. Experiments involved classifying subjects based on their MR images into HIV or control classes. Here, the output is the HIV or control, and the protected variable is age. Quantitative evaluations involved evaluating all methods using the balanced accuracy F1 score, area under the ROC curve or AUC, as well as parametrics such as a squared correlation and mutual information or MI. Our last experiment include predicting the gender of the person based on input face images. Our results again show competitive performance with respect to balanced accuracy F1 AUC squared correlation, mutual information, and equality of opportunity or EO. For details of the experiments and results on synthetic data, please refer to the paper. Thank you for listening. Please contact us if you have any questions.